One of these days, I remember Rule stopped by my room and then we were brainstorming because we didn't have anything else to do, I guess, about what to do, some new research topic. And then we had this hammer, the hammer of this iterative method that I'm going to show. So we were looking for a nail, and Rule actually suggested, why not use this for imaging microseismic data? And so that's how this work started. Let me show you this synthetic microseismic data. So can anyone guess how many microseismic sources have generated this data? I'm sure the answer is at least one. But there could be two, like there are two like prominent events there, or there could be multiple, right? And since this is not a quiz, the answer is there are two sources that generates this data. But now if you image this data, you might end up with multiple microseisms in the image. And that's an issue, right? So this is what's happening there. You're not only recording the direct arrivals in the data, but also there are scattered events. And so when you image all this stuff together, you're obviously going to get the true microseismic source location, but also these scattered events will be imposters. They will give you false positives. And that's kind of bad, because what is going to happen is these imposters, these false positives, are going to be lie at a different location than the true microseismic event. So what is going to happen is you're going to interpret the whole stimulated reservoir volume as to be bigger than what it actually is. So you, in that case, you might actually, in your next fractioning operations, you might actually bypass zones. So it is extremely important that we image all these primary as well as scattered events properly. Let me briefly recap some of the ideas that I had mentioned in the previous talk. We are going to consider microseismicity as a function of space as well as time. And here is again the microseismic data, which is a convolution of the source signature with the Green's function. And you can then obtain this microseismic image using just this deconvolution operation of data and the Green's function. But for you to obtain the true source signature, it is extremely important that the Green's function be accurate. With an incorrect Green's function, you'll end up with a lot of spurious events in this reconstructed source signature, which is obviously going to be incorrect. And so, we have to reconstruct this Green's functions accurately. However, it's not easy. Your Earth is heterogeneous. There's a variable velocity model, density model, so it's extremely difficult to obtain this true Green's function. So here we use an iterative scheme to generate this Green's function, which are then used in imaging. And I should mention that this iterative scheme, which was originally proposed by Rose, and Filippo has worked in his thesis on this, and K. Swapna actually extended Rose's 1D iterative algorithm to multi-dimensions. And here we use this iterative scheme to go from an estimate of the Green's function to estimating the true Green's function, provided that we have a background velocity model and we have reflection surface seismic data. So what you see in this figure is on the left is a direct arrival from a certain image point in the subsurface. And then using iteration, we can reconstruct the Green's function, two Green's function on the right. And then that Green's function, it's actually used to obtain the image of the microseismic source. Last year, for who attended the CWP meeting last year, might recall that we used this iterative scheme and also decompose the Green's functions into up and down going waves to image primaries as well as internal multiples in surface reflection data. For example, here is an RTM image of a fold belt. There should actually be just 4 interfaces here, but then you can see that there are multiple interfaces. But then using this imaging algorithm that we had introduced last year, you can see that the internal multiples, for example, here have been imaged properly. So we are going to, instead of decomposing it to up and down going waves, we are just going to use the Green's functions from a virtual source and record it on the surface and use that to image these microseismic events. And that's the Green's function shown on the right. So let me recap. We record the data on the surface, microseismic data on the surface, and then we reconstruct the true Green's function from a certain image point to the surface using this iterative scheme. And this Green's function reconstruct requires surface reflection data as well as a background velocity model. Okay, this is too bright, but this is an example. This is the same fold belt. There are 2 microseismic sources here represented by the black stars. And there are a bunch of receivers on the surface. Here is the reverse time image of the microseismic data. You can see that the 2 sources have been imaged at the right location as well as the right time actually. But there are many spurious events here. However, if we do the inverse scattering, use the inverse scattering approach to compute the Green's function, this is what we get. Again, the 2 sources have been imaged properly, and many of the spurious events have been eliminated. But note that it's not completely free of artifacts and spurious events. That is because you can think of that even if I have my correct Green's functions, when I backpropagate these waves, they'll still focus at the right location, but they'll still generate some of these artifacts. So it's very difficult to get rid of all these spurious events. And this result was done was generated using only 5 iterations of the iterative scheme. If we go to higher iterations, it's computationally expensive, but we might be able to get more accurate Green's functions and suppress these artifacts further. So this stuff that I just talked about was imaging surface microseismic data. Imaging borehole microseismic data might actually be more complicated because what we need for this methodology to work is we need sources at the receiver locations. So, but in the borehole we do not have such sources. So what we need to do here is we have the data represented by D from the microseismic source to the receivers. We need to compute this Green's function from this image point to the borehole receivers. And we cannot directly use the iterative scheme to do that. So what we can do is actually use interferometry to get this Green's function. And to use interferometry, we need to do one step before that, and is to compute these Green's functions represented in red. We need to compute the Green's function from the image point to the surface, compute Green's function from the borehole receivers to the surface, and then use these two Green's functions in red to, as inputs for seismic interferometry, and then compute the Green's function GIB, that is Green's function between the image point and the borehole receivers. So that's the way we can compute this Green's function in blue. Here is the same layer cake model that I had shown earlier. The black star represents the microseismic source again, and I use two different sets of borehole receivers, one vertical, the other horizontal, to get actually better aperture. And here is the image obtained from this for this microseismic event. Again, note that the horizontal axis is x and the vertical axis is time. So we are again computing the microseismic image as a function of space and time. The true microseismic source is here. It's imaged at the correct place, and this is an artifact. This line passes through the borehole receivers, so it's an artifact from there. This is kind of satisfactory, but we are not completely satisfied with it because there are artifacts on both sides of the image, as you can see, which might be because of aperture issues and of the number of iterations. There are many steps involved in generating this. And here is the reverse time image of this data. Again, these prominent artifacts are again the direct waves as well as the head waves coming from the back propagation of the recorded data. However, still the image, reverse time image, gives you the correct image of the microseismic source, and there are actually, you can see artifacts from the internal multiples. I'm still working on actually improving this image to, or the inverse scattering image, to make it better with respect to the reverse time image. As I already mentioned, for this methodology to work, one not only needs a background velocity model, but also one needs reflection seismic data, surface reflection seismic data. And it's not that common. Well, nowadays it's becoming common for people to acquire both microseismic data and surface seismic data for the same area, but it's not common. What happens, what can we do in that case? Maybe we can use passive seismic interferometry to generate these virtual source gathers, as shown by Dragunov and people in Delft, that you can generate such reflection seismic data from passive seismic interferometry and then use that data in the whole procedure. And to summarize, we need accurate Green's functions to correctly image microseismic events that have scattered events arrivals in addition to the primary arrivals. And this accurate Green's functions can be obtained from an iterative scheme and then used in the imaging algorithms to obtain better images of microseismic data of both surface as well as borehole. With that, I'll open the floor for any questions.